So, like everything in life, life isn't perfect. So what I mean by that is not everything can be done using a couple of methods. So last time we learned about the separation of variables, which is we learned in regular calculus. Uh, but there's other types of differential equations out there. So in this section, we learn about 4 different types to do so. The good thing is they're actually uniquely done based off the situation we're actually given. Okay, and we'll talk about those 4 types and how we actually use them and how we actually apply to them. Unfortunately, some of these are very, very difficult to go by because there's multiple ways to deal with it. What I mean by that is you'll be using this situation first, and then eventually in the problem, then you have to use the second situation. So there's intertwining. There's not always one proper way to do so, and you'll see that as we go into these questions. But for now, let's just write down or figure out what these actual types we're going to have dealing with. So the first type is called a homogeneous one. Is given by when our right side is equal to dy dx, and the other side is just in terms of the function x and y. Okay, so an example like this situation will look like something like that, where it's just dy dx equals, again, a function just in terms of x and y on the other side. Okay, now this is very particular because if we can express this side somehow to be a ratio of y over x only, so a situation like that, then we can use a quick little substitution for, let's say, call it z equaling y over x, and then finally we can use separation by variables if we can, and we'll do a big if, or again, this is the big one, if we can use another method. Okay, but usually when we do this substitution, most of the time a separated variable is much easier to deal with, and then we'll just re-substitute back in original concept there. Okay. That's the first type. So again, if it looks like this is probably the way they're going to go. Okay. The second part is the substitution way. Okay. So very similar to the one we just did above, where the right side is equal to dy dx, and the left side is, again, all right, so the right side is dy dx, and the left side is this portion. But here is the situation on the function itself. If, however, I can't write it as in terms of a ratio of y over x, however, it looks something like this, or kind of like that, where a and b are just some constants. So this will be 1 and 1 in this case. Let's say we don't have a variable there, or number there. Therefore, it looks like this. We call it some function g. Okay? That means we're going to have, again, another substitution, but this time the z is going to equal to the entire thing itself. Okay? In other words, we have a transformation. Okay? And then again, we'll use separation of variables if we can as well. Okay? But if you guys notice the pattern, a lot of substitution going forward. Hence the reason why it's called substitutions and the transformations. Okay? So the third way is a very unique one. This is actually very popular in mathematics. It's called the Bernoulli equations. So Bernoulli equations are any first order equations that look like this. So if you notice, this looks kind of similar to what we already had. Right? We had p of x, y, but this time the q of x is something in terms of x times a y to some power here. Okay? So the only difference between Bernoulli's equation and what we've done so far is these p of x's and q of x's are only in terms of x's. This is multiplied by y somehow, and this is multiplied by y to some raised power of n. Okay? Now, when we have this situation, and again, n is a real number, it's called Bernoulli's equation. The reason why is because we're going to do a substitution of v equals y to the 1 minus n power. Okay? And the key thing is after we divide everything by y to the n first. Okay? So what we're first going to do is divide everything by y to the n, meaning this power here, and then we'll do our substitution of this process. So it's always going to be 2 with a negative power. That's the key thing. Okay? And now the last one is the most difficult and most painful one because we're going to have a software system, and that's not always fun to do. Something called a change of variables. So if the equation has a linear coefficients of this form, so notice it's drastically different than what we have above. So biggest thing is we have a positive plus here, so most of the time we don't have there's no way we could do a separation of variables. And we have now a constant c here. Again, dy and dx here, respectively. Therefore, we're going to change x to equal u plus h and y to equal b plus k. Okay? Where h and k are constants, the problem is we have to find those constants. That's the reason why it's change of variables. Okay? Now, the way we're going to solve for this u and k respectively is to just do a system of equations where or a1, b1, a2, and b2 are the constants in front of the h's and k's, and the c values are what's equal to. So the first thing we have to do is solve for this system and then work our way backwards to do the other process. Now, when we work our way backwards, you'll go back to this situation. Again, we can either use a separation of variables, or any type of form of these is going to be applied back to it. Okay. So these are the 4 strategies we're going to try to do in this section. Again, not very fun to do, and you'll see how in a little bit. Some of them are pretty straightforward, and some are, you know, a back burner and a headache to deal with. Okay. So let's just try it going forward. Okay. So we're going to jump around when it comes to these ones. We're going to do this one first. All right, so each of these is solved for the equation. So we have dy dx minus 5y equals negative 5 over 2x y to the third. Now, if you notice, this is a Bernoulli equation. We have dy dx, check, minus 5, that's going to be our p of x. Here's the y. We have our q of x, which is in terms of x, and we have y to the n power, x to the third. So this is a Bernoulli situation. So let's just label what we know so far. So we know that p of x is equal to negative 5. We also know that q of x is going to be negative 5 halves x. Right? Okay, so first step we're going to do is divide everything by y to the third. So this then being y to the second power, and now we just get that. Okay, so now we're going to follow this process. So we're going to substitute v equals. So our substitution is going to be v equals 1 minus n. So 1 minus 3 is 2. So substitute y to the negative 2 power. Okay. So once we do that, we'll just straight substitute this portion. Okay. Now, when we do the substitution, there's a couple things. So notice this is going to be fine here. That's going to be straight v, but we have a problem here because this ends up being another y there. Okay. So to do so, we're going to do a little bit of backtracking, and we're going to do everything in terms of just v for now. Okay. So in other words, we got to find dy dx of just v or y itself. Okay. So we're going to first do dv dx. So take the derivative with respect to x itself. Okay. And this gives us negative 2y to the negative 3. And because it's implicit, because it's in terms of x, it is dy dx. Now, again, why do we do this? Is because here is our problem, right? I need to turn everything into terms of now v. So this is okay. This is the problem with the y. And again, this is the problem with because of the y values here. Now, the nice thing, if you notice, this actually gets engulfed there as well. So this entire process gets engulfed here. Okay. So it's kind of like the use substitution method when you do integration is, well, okay, what do we want? And we divide what we don't want. So notice everything gets engulfed except for this negative 2. So I'm just going to divide both sides by negative 2. And now notice this will get substituted there, and this now gets substituted right there. Okay. So now, instead of all this, I now replace it with negative 1/2 dv dx. And instead of y to the negative 2 power, it represents 2v. And everything else stays the same. Like that. Okay, so let's first multiply everything by -2 to get rid of this partial. So this becomes a positive, and this becomes a positive, and the 2's cancel. So we just get that. Okay, now you may think, okay, we just converted something that we're not sure what to do, but we actually do. We have to go back to section 2.3-ish, and what we learned is our process of our integrating factor. Okay. So this is the method of finding a integrating factor, and then from there finding our values themselves. So we got to find our u of x, and our u of x is the e raised to the integral of p of x. Now originally we had p of x here, but now we're dealing with this situation, and our p of x is here, and this is our q of x. This is our p of x when it comes to our integrating factor, so this is going to be 10 dx. So that just gives us 10x. So we have an integrating factor u of x equaling e to the 10x. So, right? So now we multiply u of x times q of x. Again, this q of x was from here, not for the original one. So I'll just get q of x1, p of x1. Then we don't get too confused. So this gives us 5x e to the 10x. And now according to that process, our v, so this v is going to equal to 1 over our u of x, which is e to 10x, times the integral of this plus c. That. Or actually, like that. Okay, so this is where, integration gets pretty hefty, because this is an integration by parts situation. So it's not too difficult. You let this be, let's say, call it w. Let's be, I don't know, whatever letter you want to call it, or dz or something like that. And you work your way backwards, and eventually, just good thing is you only have to do one integration by parts. But we actually get this at the very end. All right, so distributing this all the way through, so it's nice, these cancel. We just get 1/2 x. These also cancel, so we get negative (1/20), and this becomes plus c e to the negative 10x. We'll just keep it as a whole one like that. Okay, so now after all this, we just go backwards. We replace what we have here. So originally we had v equaling y to the negative second power, so we're just going to rewrite that now in terms of this. So in other words, just this value represents replaced. Whoops. To that. And then finally we're done. Okay. Technically, if you really want, we could just bring both to the other side, or just flip it around, so you get y squared is equal to all of this over this, and then square both sides. But that's good enough right there. That kind of makes sense for what we have to do. Okay. So that's our answer. That's good enough, at least for now, for our answer. Okay. All right, so let's go to this one here now. All right, so far we've had a Bernoulli's, right, and it kind of looked like a nice form. And for some of these, we may have to convert it into the form we want it in. Okay, So if you notice, we have an x minus y here, and we kind of have it here, right? Just flipped around. So I'm just going to rewrite this a little bit to make it look nicer to see, or visualization to see. Because if we noticed, the only ones where it has dy dx equaling is going to be these two. So it's either going to be homogeneous or a straight substitution, right? And we got to figure that out. So can we write it in terms of y over x? And it doesn't really look like I have a fraction, right? Some ratio. So it's probably going to look like this. So to do so, I need to figure out a way to rewrite it as just this format, x, y values. Okay? But it has to be the same situation in both cases. So let's see what we could do. So if I could factor out a negative from here, that means it changes the signs, and I'll keep this minus 1 there. Okay. Now it looks like we have this situation. So I have everything in terms of just x and y, the same situation we have here. So I'm now going to use a substitution of the z. Okay. So we're going to say we're going to let z equal x minus y. Okay. All right, so if I now substitute this into here, and now I also, just like last time, I got to rewrite this portion here. So I'm just going to take the derivative of both sides with respect to x. So this ends up being dz dx is equal to 1 minus, this is just 1 times dy dx. And if I solve for this, it just ends up being dy dx is equal to 1 minus dz dx. Okay. So now I'm going to substitute this and that respectively for each one. So that and that. So this entire equation, this becomes 1 minus dz dx is equal to negative z minus 1 plus z plus 2 raised to negative 1 power, which looks a little nicer to look at now. So first off, I'm just going to make this positive because this is not fun to do. So I'll subtract this 1 over and multiply by negative. So subtract this 1 gives you a negative 2, and then multiply everything by negative 1 makes positive, positive, negative. Okay. All right, so now the question is, what do we do now? So again, somehow, since everything's in terms of z, maybe we can use separation of variables, right? That's the whole point. According to our rules here, we can transform it and somehow use separation of variables. So let's see if we could just put this stuff together. So remembering that, I'll keep this in parentheses, it's over 1 minus 1 over all of this. So I could technically put these together by just common denominators. In this case, our common denominators will be just z plus 2. So multiplying top and bottom by z plus 2 and this by 1, we're just basically squaring it. It gives us that. Alright, so now I can actually use separation of variables. So if I multiply both sides by the bottom and divide everything over, they just flip-flop. I get that. Now you may think, oh, this is maybe more work than you actually have to. But again, this is where integration, well, it kind of tests your integration, let's just say, from previous classes. So we're going to let u equal the everything on the bottom. And we take the derivative. This is 0, derivative inside just 1, so we just get that. And notice this is exactly what the top is. Well, here, we'll just take the integral. This is just going to be 1, right? So we just divide by 2 to get our situation. So we have 1/2 du is equal to z plus 2, which is, again, what I have on the top. So this substitution method ends up being like that. And then, this is kind of nice to do. All right, so this is just ln. This is just x on this side. And then, remember, the whole point is actually to solve for this back situation, right? So we will rewrite everything in terms of u. Now, I'm not actually going to plug in what z was to begin with just yet, because I do want to solve, because it makes it really messy with all this minus plus stuff. So why don't we just figure out a way to go from here. Actually, we could have stopped here and just did it there, but this is technically the full u substitution method. All right, so we want this by itself, right? We want to solve for z, let's just say, for instance. So we're just going to use our properties of log and bring this here. Or actually, yeah, we'll just do that. Yeah, we can't divide it over yet. So this ends up being that. And now we're going to take the e to both sides, so raise everything to the e power. All right, so ln's cancel and e's cancel, so we just get yeah, I guess we could do that. Yeah, it'd probably be easier if we just did it here. It's okay. And this simplifies just that. Okay, so we're going to square both sides to get rid of this 1/2 power. So we just square both sides. And then squaring this just gives you that, right? C squared is just C. It's just still it's just a constant. Adding 1 over. Gives us that. And I don't want to take the square root because that's going to be plus or minus. We don't want to deal with that too much. So we could stop here and then just work our way backwards. So again, originally z was x minus y. So if we just replace it, we get our final answer. There we go. So that's how we do the substitution method. Okay, so now let's try the one underneath this. Okay, so we have dx dy here. So let's go back to our notes. Which one this kind of looks like? So it kind of looks like this one, which is not fun to do. Or it could be any of them, right? If we could somehow manipulate it in a way we could do it, so that would be kind of nice. So let's try this out. So this is not ideal, right? This would be last resort, so maybe we can manipulate a way to just have dy dx in some situationships. So let's see. Okay, so we have this, so why don't we just add this over. Okay, so now if we just divide everything over, so meaning just divide the dx over and divide this all over there. And let's see what we get. Okay, so we want dy dx, so divide. Okay, let's see if that looks any nicer to deal with. We can simplify this a little bit because it's just one term, so we could just separate this addition on the top. And I'll simplify each one. And we get that. Okay, so what do we do at this point? Well, remember the whole point is not to do separation of the last situation, which is the problem. But our first type was the homogeneous one, said if we have one side is equal to a ratio of y over x, then it's going to be homogeneous. And it looks like that we have y over x here, y over x there. So therefore, it's going to be the first situation where we do is we use the substitution z is equal to y over x. All right, so let z equal y over x in this situation. So we get z plus z squared plus 1 equals, oh, now we got to figure out what this is. So why don't we just quickly just multiply this over. I really don't want to take the derivative of this mess over here exactly. Yeah, let's do that first. So let me put that over here. Multiply both sides by x. And now take the derivative with respect to x. This is going to be, this is product rule. Gives us that. Okay, so therefore, here, write this here. Now I substitute all of this for that. Okay, so let's do that real quick. Now at this point we should be able to do separation of variables, we hope. Let's see, so I could subtract the z over. So now we have that. Okay, so if I could bring that over there. Oh, it looks like we can now. So divide over the x, divide this over. We have 1 over x dx is equal to 1 over z squared plus 1 dz. And there's our separation of variables. Good. All right, so not too bad. So now we take the integral of both sides. Okay. So again, this ends up being ln of x, or in this case, ln of x. And on this side, this is a very famous one. This is tan inverse. So if we just a quick little note, that is tan inverse, that property. So this is just tan inverse of z and now I want z by itself, so I just take tangent of both sides. And then finally I just replace z with what originally was y over x. And this one's not that bad to solve for y. We just multiply over the x, and we are done. Okay. All right, so it looks like we've done 4 so far, and we're down to 2 more. Now, I will admit, the last 2 are the most difficult to deal with. Okay, so why don't we try this part, I guess. Here, we'll do this one first. Yeah, we'll do that one. I'm going to need extra space as well. Okay. All right, so this is kind of looking like what we did up here with the substitution method. It kind of already pretty much shows you, right? If we just substitute x plus y to be our z portion. So this is a substitution 1. So we'll use z equaling x plus y. So now if we rewrite this, so now it forces, because if we take the derivative, we need dz dx and dy dx. So we need dy dx. So divide this over, divide that over. Okay. All right, so going back over here, taking this derivative with respect to x. So therefore, if I just subtract this 1 over, dy dx is going to equal to dz dx minus 1. So that's where I substitute here for that. Okay, so once we do that, this equation looks like that. Add over the 1, and I'm going to change this to tangent. Gives us that. And again, this is nice because it is a separation of variables. I can multiply this by dx and divide this all over, and it ends up being 1 over tan z plus 1 dz is equal to just dx, or just 1 dx. And now we take the integral of both sides, and this is where it gets a bit of a problem. So, partial fractions. The only way to do this integral is to do partial fractions. Okay, believe it or not. Okay. So, after a lot of partial fractions in situations and in finding the a value, the good thing is there's only two of them. It's just in terms of a sine and cosine. Taking the ln of x and all that integration process, fun stuff, or you could just memorize this. This right here is basically a property. If you guys want to go back to your integration rule book, it gives you this. And this is just x plus c. Okay. Multiply everything by 2. Two times c is just still gives you the c value. And now resubstituting what z was to begin with, which was just x plus y. And this is, again, all we can really do. Not so fun because of this partial fraction one. Okay, so let's go to the last one we skipped. For a reason. Alright. What can we do here? Okay. Now, this is actually going to be our fourth type of one, change of variables. Okay. And it follows the same template because we have a c value there and there. Okay. So according to our change of variables equations or situation here, we're going to let x equal u plus h and y equal v plus k. Right? And now we have the system of equations here. So we're going to have 2h b1, so minus 2k is equal to negative 6. Then we're going to have 1h minus 3k is equal to negative 5. Okay. Now, one thing I didn't say is about the situation of the change of variables. Technically, what it really is supposed to look like for both of them are these two. Okay. So what that means, when I bring this over, it just changes the sign. Okay. So technically, it is a negative 6 and negative 5, but because of this is the actual transformation, all we're going to do for the c values is just flip the sign. which means this becomes positive and that becomes positive now. Okay? So it's just a subtle hint. One thing I forgot to put in the notes is just remembering that these are the opposite sign. All right, so now that we have this, we have to solve for the system. Either way you want to do it, substitution or elimination, it really doesn't matter how you decide to do it. It's going to give you the same answer in either way. So I just use elimination, just multiply by -2 and just solve for k, and then went backwards to solve for h. But in the end, you get h is 2 and k is -1. Right. Okay, so what does this mean? So this is going back over here saying that x is equal to u plus 2 and y is equal to v minus 1. That's what that represents now. Okay. All right, so that means everywhere I see an x, I replace it with that, and everywhere I see a y, I replace it with this one back into the original equation. So here, here, there, and there. Okay. All right, so now once you plug it in and a lot of distributive property and a lot of simplifying and collecting like terms, we eventually get, again, back here, this situation. Oh, actually, before I get that, no, I'll talk about that right now. Okay, so like everything else of these questions, we have a bit of a problem, right? We have this situation here. Okay, so this goes back. Okay, I want just everything in terms of dx dy. So if I just bring this over and do some division, we eventually get something like this. Okay, now again, we have to figure out this portion, but we're going to go back here and use our substitutions. Okay, all right, so how are we going to do that is a different story. All right, so for this one, now we're going to go back to original and just take the derivative respectively. So if I take the derivative with respect to x here, this is going to give me dx, or just 1, right, is equal to du. If I take the derivative with respect to y, it just gives me dv. Now this is kind of nice because this is a one-to-one relationship between the dx's and dy's, meaning this ends up just being a straight conversion. Oh no, I had it right. V was on top. Yeah, which is also kind of nice, right? Yes and no. So this is the reason why this is the last question. This is nice, going from one-to-one. But remember, now this is my problem. I'm trying to solve for this. And unfortunately, this is not a separation of variables because it's actually impossible to separate these variables together to get one side all v's and one side all u's. So we have to use another situation. So the question now becomes, which one of these, besides this one, will work? Meaning which one of the three. Okay. So that's where we have to do a little bit more finessing. Okay. So one way of finessing is I'm going to multiply top and bottom here by 1 over u. Like that. So now when I multiply top and bottom by 1 over u, these u's cancel. These u's cancel. And we get that. Now if you notice, this looks very, very familiar to what we just did down here. Oh, no, sorry. Here's our first one. Where is it? Where is it? Oh, yeah, right here. This one. Where we had ratios. So for the ratios, it was actually a homogeneous. Okay? So if we have a ratio of y over x on one side, we use our substitution as z equaling to, and then use hopefully separation of variables, or again hopefully not another method, but hopefully separation of variables actually works out here. So that is exactly what we have to do now. So this is a not so fun one, right? Happy with smiley face or sad face and stuff like that. So I'm going to let's say call it z equaling v over u. So now these become b's, but I got to figure out what this is. So we'll do the same thing we did on that question. Multiply this by u. And now take the derivative with respect to u to both sides. So we just get z plus that. Okay, so now we're going to substitute this and this. Oh, sorry, for this. And we get okay. So subtracting the z to both sides. I'm going to leave the u there, and you'll see why in a little bit. Putting this together. So collecting like terms, so multiplying both sides by this process because we want common denominators will give us this on top. Z, not W. Okay. And now this is good because all this is in terms of Z, just U. So all we have to do is make a little bit of maneuvering, right? We want U's on one side, U's everything. So I'll bring du over here, bring this all over there, and then divide this all over. So a lot of dividing, a lot of maneuvering. But eventually, we actually get all z's on one side, all u's on the other side. So this ends up being that. Okay. So integrating both sides here. Again, this is going to be natural log, so it's not too crazy. But the other side, however, follows the same pattern as the previous example. The only way you could do this is actually doing partial fractions. Okay, so after doing a partial fraction breakdown, it doesn't get any nicer. It eventually gives you this. And after taking the integral of it, I'll put rather than a space here. Now at this point, you can technically simplify some more. You could put this together, so this will go here, that will go there, and then put these together, then raise it everything to the e power, and eventually you could solve for one of them. But it's just messy all the way around. So at this point, all you could really do, or if it's just easier, just plug in what the original values were. For instance, z was v over u, okay? But we want everything in terms of x and y, so we just work our way backwards. So we just want to figure out what v and u are respectively based on what we have. And that means we go back here. So we just solve for u, so that's going to be x minus 2, and we solve for v, that's going to be y plus 1. So now we just revert everything back to its original. So for example, on this side, you'll have ln of u is equal to, on that side, and again, instead of z is this fraction, and again 3 times this fraction. And I think that's good enough. Again, technically you can go farther. You know, it ends up being a nicely where everything's in terms of just one side equal is just x and y, and the other side is literally just a constant c. But it's a lot of algebra at this point. Okay? But you could technically go farther down to get the exact value you wanted to. But it is what it is.